Good morning, my algebra friends. I'm sorry I'm not with you in person today, but this will be fun, for me at least. Thank you, Mrs. Young, for subbing for me today. So, folks, if you want to get out your homework, I'm not there to see how many of you got a plus, a minus, or a check, but maybe Mrs. Young can count the number of folks who have a plus, a minus, and a check. Maybe pause this and do that so that you can send that information to me so I can know how they did with their homework last night. All right, today we're going to go over the homework and then we're going to introduce the next two sections. The first one will just be a review, kind of combining all the different types of factoring that we've done so far. And then the second one will be solving equations using factoring, which you're going to find very easy, I think. So I'm excited about today. Let's go ahead and get started. On your homework, number 9, we had 2x times x minus y plus y times y minus x. And our goal here is to factor this thing by grouping. So as we look at this one thing you might notice is that these two look a lot alike. And if we want to factor it out of this polynomial, then we could flip one of them by multiplying by -1. You may remember that. So if we do that, we're going to end up with 2x times x minus y minus y times x minus y. How did that happen? Well, we multiplied a -1 here across this entire monomial. So this y turned negative, the x that was negative turned positive, and the y that was positive turned negative. Now we can factor out the x minus y. And if we do that, we're left with x minus y factored out. And then what's left is going to be the 2x and the -y. So we can write 2x minus y as our other factor. So if you got this right, you should have the quantity x minus y times 2x minus y. And you could, of course, reverse the order of those. That would be fine. Okay, number 11. We start out with a problem, 2u times u minus 2v plus v times a quantity u minus 2v plus, again, u minus 2v. Enough already. So let's not forget as we do this at the beginning that when there is a blank beside a binomial or a trinomial or any other parenthetical statement, you can remember that there is an invisible 1 there. That's going to come in handy as we're doing this. So as we look at all of these terms, 1, 2, 3 terms, we can see that they all have one common factor. What is that common factor? It's u minus 2v. Remember, the first step is always to look for common factors that you can take out. So I'm going to go ahead and take out u minus 2v. We factored that out. So one factor is u minus 2v. It was multiplied against all 3 of these to get this polynomial. Once I do that, what I'm left with is 2u plus v plus 1. Those are the factors I have left. And now we've factored this as far as we can. These are both prime, and that's your answer. U minus 2v times the quantity 2u plus v plus 1. Looking at 13, we start with x times the quantity 2w minus 3v plus u minus the quantity 2w minus 3v plus u. I love it when things look the same. Makes it easy. Again, let's not forget that there is a 1 there. And now we can look for the common factors. You're always looking for that greatest common monomial factor. In this case, it's a polynomial factor. And we're going to take that out. 2w minus 3v plus u. Because we've divided by it, we factored it out, we're left with what we have here, x minus 1. So if you've gotten that one correct, you should have the answer, the quantity 2w minus 3v plus u times the quantity x minus 1. All right, let's look at number 15. We've got the quantity x squared minus 2ps plus 2s minus the quantity 2s minus 4p plus 4. All right, don't be freaked out at this subtracting of two trinomials. No big deal. What we want to do is find the common factor that we can pull out of this s squared minus 2ps plus 2s. And what would that be? Looks to me like it's an s. If I do that, the s squared divided by s leaves us with, whoops, that's no good. Erase that too. That leaves us with s minus 2p plus 2, close that parentheses, minus the quantity s minus 2p plus 2. Oh, I need to show you that I took a 2 out of there. Sorry about that. So a 2 came out of this one. You see that? We divided the 2. If I do that, then I'm going to end up with s minus 2 times the quantity s minus 2p plus 2. Here's the 2 that we took out that ended up here. All right, let's look at number 17. We start with 3t minus 3st. We're multiplying that binomial. Well, we're adding it. Pardon me, we're adding that to the quantity rs minus r. Remember, we have to factor each one of these separately. We can't factor out something from both binomials and put it over here. Each one has to do its own factoring. So we're going to look at the 3t minus 3st, and we can see that we can divide both of these factors, or these terms, pardon me, by 3t. So we're going to write 3t here because we divided that, we factored it. That leaves us with 1 minus s. Now let's do something with this one, rs minus r. We see that r is a factor of both of those. So we factor out the r, and oops, that's not an r. We're left with a 1. Yes, when you factor out that r, you still have a 1 because it's 1 times r that equals r. Don't let 1 become an invisible factor. So here we are, 3t times the quantity 1 minus s minus r times the quantity s minus 1. Well, the thing is, I can see that this one and this one, these two binomials, are the same in reverse. And you may recall from the first problem in your homework that we can multiply a negative 1 to flip that second binomial. So let's do that. That'll make this a lot easier to factor. We can do 1 minus s plus, oops, now it's not plus, is it? Let's erase that, and let's get this right. Because we're multiplying a negative 1 across all of these terms, this r becomes negative, the s becomes negative, and the 1 becomes positive. And now we have a common factor we can see quite clearly. So we can pull out the 1 minus s, we factored that. Then we're left with the 2 remaining terms, which become the other binomial in these two binomial factors, 3t minus r and 1 minus s, and that's your answer for number 17. We'll look at 19. We start with 12x squared minus 8xy minus 5 times the quantity 3xz minus 2yz. Okay, we're going to factor each of these big terms by itself. Then we'll look at the whole thing. So let's look at this first one, 12x squared minus 8xy. I can see that 4x is the largest common factor. Once I take that out, 12x squared divided by 4x is 3x, minus 8xy divided by 4x is 2y. And now I'm ready to look at this second term. Well, we have, oops, I'm looking at my own work and seeing a possible mistake. 3x minus 2y. Oh, no, I see it. Okay, so our greatest common factor here between 3xz and 2yz is z. Got to bring that 5 down. That's what was throwing me off. I was like, where'd that 5 come from? Oh, yeah, it was up top. So we pulled that 5 down. We factored out the z. 3xz divided by z is 3x, minus 2yz divided by z is 2y. So now we can see we have, lo and behold, the people who write your book are very kind to you. They leave you with these binomials the same. That's great. That means I can factor it. It is a factor of this, is a factor of this. And so now 3x minus 2y, just one of them, because I divided 5z times 3x minus 2y by 3x minus 2y, leaving me with a negative 5z. I divided 4x times 3x minus 2y by 3x minus 2y. That's why this is here. And then I'm left with 4x. There's your answer. 4x minus 5z times 3x minus 2y. All right, 2 more to check on this homework. We've got number 21, 3a plus ab plus 3c plus bc. Okay, the very first thing I want to do here is factor out what I can. I'm going to group these because I noticed that these have A and B and these have C and B. So let's make this a little bit easier by grouping and then factoring the ones that have a common factor. So I see 3a plus ab has a common factor of A. Factor that out. If I do 3a divided by a, I get 3. ab divided by a, I get b. And then if I see that c is a common factor in this binomial, I can divide by c, and I'm left with 3 plus b. Oh, authors were kind to us again. If we divide both of these by 3 plus b, the leftovers are a plus c, and we've divided or factored 3 plus b. Look at that really clean answer from this problem. Don't hit the panic button when you see these. They always have an easy way for it to work out. So x squared, number 23, last one. X squared minus 2x plus xy minus 2y. Again, looking at these, I'd like to group them so that I can factor something out of every single term. The best way to do that is to take these, excuse me, that both have an x, these that both have a y. Now the temptation would be maybe to make a trinomial of this, this, and this, but that's not going to make my factoring any easier. Let's just do with these two binomials. So if we do that, I can take an x out by dividing x squared minus 2x by x, leaving me with x minus 2. And then, out of the second term, we can see that a y is a common factor. So we'll divide by y, leaving us with x minus 2. Ah, exciting. X minus 2 is a factor of both. So I can divide that, pull it out. I'm left with x plus y. X minus 2 times x plus y. Oh, look, I was wrong. You guys have 3 more. I didn't flip my paper. Okay, 25. We start with h squared minus hk plus hr minus kr. Well, again, I'd like to group these so that I can take a factor out of each pair. Looks like I can do an h here. H squared divided by h is h. Hk divided by h is k. Plus, looks like we've got an r in common here. So I can take an r out. I've divided by r. I'm left with h minus k. And, again, h minus k is a common factor. That being the case, I'm left with h plus r times h minus k. All right, number 27. P to the third minus 2p squared plus 4p minus 8. Can you see where we should group these? I'm seeing that. If I do that, I can take a p squared out. So if I divide this by p squared, I'm left with p minus 2. And then this 4p minus 8, I can see a factor of 4 is the greatest factor I can work with. So it's going to leave me with a p minus 2. Look at that. Very predictable, isn't it? We're left with p squared plus 4 times p minus 2. Now, before you get all excited and see two squares here, I mean, that is exciting, but it's not a difference of two squares. So you're going to have to leave that one alone. You can't do anything with it. It's p squared plus 4, p minus 2. I know if I were in there and were asking how many of you tried to treat that like a difference of two squares, Corbin would have done it. All right, let's look at the last one. This one really is the last one before we look at this next section on combining all the different ways of factoring. P squared minus 2pq plus pr minus 2qr. All right, this looks like the last few ones. We can't take the same factor out of all of them. They don't all have a p. They don't all have a multiple of 2. They don't all have a q or an r. But I can see that these two both have p. I can work with that. What did I do here? PR minus 2QR. Oh, we have an R there, I see. So these both have an R. All right, so let's handle the first one. Looks like P is our greatest factor that they have in common. So P squared divided by P is P. 2PQ divided by P is 2Q. Here we can factor out an R from this term. So PR divided by R is P. Minus 2QR divided by R is 2Q. Look at that. Now we're left with P plus R as our first factor, and P minus 2Q as our second factor that both are divisible by. And there you go. Easy as that. All right, we're ready for what's next. All right, look at page 227 for a second. I want to show you a handy tool that's in your book on page 227. It's this Guidelines for Factoring Completely. All right, pardon my sloppy handwriting. If you could learn this gray box, it will be your friend. Now, some of you may know it instinctively, but if you don't, this is a really nice place to kind of use as a cheat sheet, the most ethical cheat sheet I will give you. So first, you're going to factor out the greatest monomial factor. Well, we've been practicing that. We've been looking for the greatest monomial factor. Sometimes we grouped first because we could see there wasn't a common monomial factor for all of them, so we grouped them such that each binomial we created had a common monomial factor. If you see a difference of squares, Remember, that's a subtraction, right? A difference where the two terms are squares. They have a nice clean square root. So this would be an example, right? X squared minus 4. If you see something like that, well, that's easy because then you can do the whole x minus 2, x plus 2 thing. Look for a perfect square trinomial. If you have a perfect square trinomial, that's the squares on either end when the trinomial's in standard form. So in the quadratic term and in the constant term, or the last term. If a trinomial is not a square, look for a pair of binomial factors. If a polynomial has 4 or more terms, look for a way to group the terms in pairs or in a group of 3 terms. That's a perfect square trinomial. You can always rearrange as long as we're following the rules that we've learned in the course. If each binomial or trinomial factor you've come up with is prime and you can't factor anything else out, that's what prime means, then you can just check your work. Multiply all the factors that you have on your last line of work and see if you don't end up back at the starting problem. If you do, then you've done it correctly. That's just handy on page 227. If I were you and I was a little uncertain about these, I would look at that when I'm working on my problems. All right, let's do a few samples where we take everything we've learned about factoring and we combine them into one. So this is nothing new. This is just you applying the things that you've already done. So let's look at this first example. Negative 4n to the fourth plus 40n to the third minus 100n to the second. All right, I'm going to look across these for the greatest common monomial factor. Greatest common monomial factor. Well, I see that they're all divisible by 4. Also, these n's are all to the power of at least 2. So 4n squared is my greatest factor of all of these. So I can divide by 4n squared. I'm going to pull that out, and I'm left with n squared, because negative 4n to the fourth divided by n squared is negative 4n to the fourth divided by 4n squared is negative n squared. And if I divide 40n to the third by 4n squared, I end up with 10n. And if I divide negative 100n squared by 4n squared, I get negative 25. That n squared divided by n squared gives us 1. So we're left with this. Well, the nice thing about this problem is that this looks pretty clean to factor, doesn't it? Certainly does. So in order to factor that, oh, look at my problem here, make sure I did the right thing. I had to get rid of this negative. How do I get rid of this negative? This one. Because a square that's negative is going to be messy. Let's go ahead and multiply this whole thing by a negative 1. If I multiply that by a negative 1, that's going to make it a lot cleaner for factoring. So as I do that, my 4n squared becomes negative because I've got to multiply negative 1 across all of this. And as I do that, everything inside the sign changes inside these parentheses. That's now an n squared. Then it's a minus 10n, not plus any longer. Then plus 25. Great. This I can handle. I know, because there's no constant, no coefficient term here, that I'm going to have an n in each of these binomials. Remember, now we're factoring this polynomial. We did these like 3 lessons back. We want 2 factors of 25 that add up to negative 10. 2 factors of 25 that add up to negative 10. Well, what would those be? If they're going to add up to negative 10, they both have to be negative, don't they? Well, looks like negative 5 and negative 5 would accomplish both of those needs. They make 25 when we multiply them. And when you add them, you get negative 10n. So we've now factored that polynomial, and we're left with negative 4n squared times n minus 5 times n minus 5. Now you can clean that up just for aesthetics and turn that to n minus 5 squared, like that. Let's look at another example. See, nothing there was new. This is stuff that you've been doing. We've just combined a few concepts into one problem. So this one, 5a cubed b squared plus 3a 4b minus 2a squared b cubed. Great. First step, find that greatest common monomial factor. Well, looking at this one, I think that we might have a squared b as our greatest. I don't see in the 5, 3, 4, or 2 a common factor. So I'm not going to have a coefficient common factor. Just going to have to look at the variables. Looks like a squared b would be the highest we can go. Well, that, if we divide 5a cubed b squared by a squared b, then we're left with 5ab. Everybody see that? If we divide 3a 4b by a squared, wait a minute. I can't do that. Hold on. I'm following my notes from when I did this yesterday to make sure I could do this screencast smoothly. I see what I did. This didn't make sense, did it? You guys have been sitting there catching it. That's the flaw in this approach. This 4 is sloppy handwriting on my paper. This 4 is an exponent. Oh my goodness, now it makes sense. Okay, so that goes up there. I'm gonna have to erase this so that it's cleaner than that. Oh wait, that's spray paint. I'm learning to use the app. Okay, we're gonna get rid of that. It's 3a to the 4th b. Now the world is right. Okay, so now this makes sense. 3a to the 4th b divided by a squared b gives us 3a squared. Now we're tracking. If I take 2a squared b to the 3rd and divide that by a squared b, I'm dividing these two now, then I'm left with 2b squared. Great. We're one step closer. We got the greatest common monomial factor divided throughout that whole polynomial. Now I'm going to have to factor this trinomial. It's my only option. I can't factor any other greatest common monomial factor because we already did that. So this is that process where you make your column. You guys remember this? I know that my factors, first I want to rearrange it and get it maybe in standard form. So let's do that. Let's carry this down and let's make this look like a typical factoring problem. So 3a squared, we want our squares on the ends. That's how all of these are written in standard form. Squares on the ends and 5ab in the middle. I didn't change any signs. Make sure we kept all the signs the same. Now we're going to factor it this way. All right, so let's make our list of factors. For 3a squared, this is a separate thing we're going to do on the side here. For 3a squared, it's 3a and a. So we know that at the beginning of each of these binomials, we'll have 3a and a because these two times each other will give us this factor, or this term. Okay, so now we've got to figure out what factors of negative 2b squared we want to choose from in order to multiply it times these and get this answer. So we know negative 2b and b would give us negative 2b squared. We know we could change that order, b and negative 2b. We know we could have the 2b be positive and the 1b be negative. We know that we could have the negative b first and the positive 2b second. And by that, I'm talking about whether it goes in this binomial or this binomial. Well, if we check our math, we know that we have to have the negative b here and the positive 2b here. Now we can do this distribution, or as some of you call it, FOIL, to check this. So let's see if we can get back up to that answer. 3a squared there it is, 3a squared, minus ab, and plus 2b, wait, hold on, 3a squared, I'm going to write it down here, 3a squared minus ab, I did these two, and then I'm going to do this one, minus 2b squared, and then I'm going to do this one, 3a times 2b is 6b. Okay, I've got my four terms. I multiplied, distributed all of those. Now let's combine. 3a squared. Forgot my a here. 6ab. Now I'm going to combine these two ab terms. I get plus 5ab minus 2b squared. Does this look the same as this? 3a squared minus 5ab, I should go further up, minus 2b squared. Yes, it's the same. And by the way, that b should be right there. That was about the sloppiest problem we've done today. But it checked out, so now let's clean this up. We're bringing down a squared b, and we factored out 3a minus b times a plus 2b. There's your nice clean answer after all of my chicken scratch. All right, let's do one more example before we set you loose practicing. We're going to start with a squared b c minus 4bc plus a squared b minus 4b. All right, well, we want to look for a greatest common monomial factor. We also might need to group those that have a lot in common. Let's see. Here's what I see. I see that there's a b in common with every single term. And if I do a squared bc divided by b, I'm left with a squared c. If I do minus 4bc divided by b, I get minus 4c. If I do a squared b divided by b, I get a squared. And if I take minus 4b divided by b, I get minus 4. Now, I want you to notice something here. Before I draw another parentheses, do you see a difference of two squares that we could group by itself? I'm imagining all of you saying yes, you see it right there. Be a good idea to take that out and factor it by itself, wouldn't it? And then we could close this one with this parenthesis. So now we've got a pretty clean problem. Let's see if we can take it a step further. So we've got a b that we've already factored out. And because this thing is going to become kind of its own animal to work with, I'm going to do one of these squared brackets, because inside of it, we're going to factor a couple of different terms, and that's going to keep it clean. And remember that this b belongs outside of all of it. So that's why we're drawing this extra square bracket. So I'm going to factor this one. And if I factor c, because I see that's the greatest common monomial factor, I'm left with a squared minus 4. A squared c divided by c is a squared, and minus 4c divided by c is minus 4. Can't forget this plus, so let's leave this plus here. Got to keep it. You can't lose signs like that, or you're going to get in trouble. All right, so we've got a perfect square there. We know how to factor a perfect square, so that's going to be a minus 2, a plus 2. Lovely. And we can't forget, we've still got this. Now the other nice thing is that this right here is also a perfect square. In fact, it's the same one we just dealt with. So let's write this whole thing out with that factored. A minus 2, a plus 2. There it is, factored. Plus a minus 2, a plus 2. Well, this is starting to look very redundant. And that's good because this little sum here means that each of these terms, I'm going to put a box around it, each of these has some common factors. And what are those common factors? Well, they're a minus 2 and a plus 2. So we can factor out a minus 2, a plus 2, because each of these has those. Don't forget the 1 that is to the right of this plus sign and in front of the a minus 2. We have to keep that 1, and we have to keep, there's a C that I left hanging somewhere. Oh, up here, see that? I almost forgot that C. I turned it into an A down here. You're probably yelling at me. So I'm bringing that C down, and I still have C, this C, plus the 1 that's over here. So I have C plus 1. And what else do I still have? This B that's been hanging out outside that square bracket. Well, there's your answer. All of these are prime. There's nothing else to factor out of C plus 1 or out of A minus 2 or out of A plus 2. So it's B times the quantity C plus 1 times the quantity A minus 2 times the quantity A plus 2. Okay, I'm out of breath from that one. All right, here's what I'd like you to do. Why don't you practice this by going to page 228, and you're going to do, I'll write this down, page 228, 7 to 19, odd. If you take about 10 minutes to work on that and check answers with each other, Mrs. Young, if you want to pair them in 2s or 3s, that's fine. We want to find out if we've got a minus, a plus, or a check understanding of these. And once you feel like you've got everybody at least halfway between a check and a plus in your confidence, then you can move on to the next section. So you might want to pause the video here and go ahead and do that. I've given you the odds, so all the answers are in the back. So let's do that. Okay, so you paused it. I'm hoping that you've still got some class time left and you're coming back ready for more. I'm turning my pages to get to the right spot for showing you how to solve these equations. This really, you've already done the hard work for today. This part's not bad at all. So when we're solving equations by factoring, where's my work on this? Oh, I skipped a page. Okay, I got it. Thanks for bearing with me. This next concept is on page 230. So this is section 512. And this is going to be pretty quick and dirty, and then you're going to get busy on it so that maybe you won't have homework. So I'm going to do 3 examples with you, and then I'll give you an assignment to work on, maybe 4 examples. Right now, if you want to write this down, your homework is, or if you finish it at the end of class, it'll be page 232, 11 to 23, odd only. And then the other thing I'm going to want you to do that you'll find pretty quick is that chapter review on page 240 and 241. You'll do all of those. And if there's any work to be shown at all, show your work. Why? So that you can figure out where you went wrong, so that I and your colleagues in the class can see where you missed something and can help you. Okay, let's look at an example here. What we're trying to do now is take everything we've learned with factoring and be able to solve an equation that has these polynomials or in it. So here's an example. You'll find this rather simple. We've got 2 binomials multiplied times each other and they equal 0. And this equaling 0 thing is important. In all of these, you're going to try to set this thing equal to 0. These are simple equations. applying the multiplicative property of 0. Multiplicative property of 0, what is that? Well, it's something so obvious you wouldn't think to state it. If A equals 0 or B equals 0, then the product of A times B will be, well, I don't know, 0 times 0, which is 0. And then the other conclusion we can draw from that is that if the product of AB is 0, then either A equals 0 or B equals 0. One of those has to be true if, as factors, their product is 0. So here we have an A, here we have a B, symbolically. And if x plus 2 times x minus 5 is going to equal 0, then either this x is negative 2 or this x is 5. We can see that negative 2 plus 2 is 0. And if this were to be 0, then this whole thing would equal 0. Or if this x were 5, then 5 minus 5 is 0. And if this is 0, then the whole thing would equal 0. So the way you write this is you say the solution set, because it's not just one answer, it's either of these could be possible. The solution set is either negative 2 or 5. So one of those two would solve, either one. That's your answer. Solution set is negative 2, 5. So to show that you're drawing a solution set, you just make these symbols. And that's it. That's how you write your answers. So there'll be more than one probably on most of these. So that was your first example. Here's another example. 5n times n minus 3. This one's just slightly more complex because there's one extra factor here being multiplied to get to 0. We have this one in addition to the two binomials. Well, that's no big deal. So if 5n were 0, would this whole thing be 0? Well, sure it would. It wouldn't matter what was in here, because if they're all multiplied times 0, if it was 0 times n minus 3 times n minus 4, and it equaled 0, you would know that no matter what the n is valued here, this 0 is going to destroy it. So we're left with 0 regardless. So 5n equals 0. We want to set that to 0. And we want to see what it would take if n minus 3 were to be 0. And how could we make n minus 4 0? Because if any one of these was 0, then this equation would be true. So we solve each one separately. You isolate your terms and you solve for n in each of them. And you have to create a 0 term. So if in this equation 5n equals 0, then n would have to be 0. In this equation, n minus 3 equals 0. I know you know this in your head, but let's just, some of the equations might be more complex. In order to get n by itself here, you'd have to do what? You're brilliant. Add 3 to both sides. So we're left with n, because this was 0, equals 3. And is that true? If n were 3, 3 minus 3 would equal 0. Yes. And so this one, we're going to have to add a 4 to both sides. We get n equals 4. So your solution set is 0, 3, or 4. If in this original problem n equaled any of these, then the whole thing would be true. So there's your solution set. Okay, now once in a while, we have something called a polynomial equation, where both sides of the equation are polynomials. When you're dealing with polynomials, sometimes you'll spot them, but they won't be in standard form. So here's the next example. 2x squared plus 5x equals 12. Now remember, you want to get this whole thing equal to 0. And you're going to be factoring in each of these. And you want the whole thing equal to 0. Well, let's make it equal to 0. How'd we do that? Well, we can subtract this 12 from both sides. And that'll leave me with 0 on the right side of the equation. So 2x squared plus 5x minus 12. Here we are in standard form with a quadratic term, the squared term here, the coefficient with the variable here, and the constant here. That's standard form. So now we can factor this. Well, in factoring it, this is going to be one of those set up the columns because we need factors of 12 and factors of 2x squared. Well, the 2x squared is pretty easy. We know we want 2x and x. By now, I hope you're seeing that and getting kind of automatic with it. But then the factors of 12, well, doggone it, there's a lot of those. So I could do 4, negative 3. I could do negative 4, 3. I could do 6, negative 2. I could do negative 2, 6. I could do, remember, because that's just the order. Do you place it in the first or second binomial? I could do negative 6, 2. I could do 12 and 1. Well, I can't. It's got to be negative 12. So I could do negative 12 and 1. I could do positive 12 and negative 1. So I've got all these possible solutions, and you know the routine. You've got to multiply times the terms that would be in the other binomials, and let's see which ones give us the right answer. Well, I went through it, and I came up with negative 3 and positive 4 here, because that gets me, if I check this, it gets me back to 2x squared. That's by doing the whole FOIL thing, or as James would say, FOIL. So we multiply all those, and we end up with 2x squared plus 5x minus 12. I got the right factors. So now that I have the right factors, I need to write two equations, because remember, I want to set each term equal to 0. Each factor, as it were, equal to 0, because these are multiplied times each other. And the whole thing equals 0, right? I should have carried that down to remember that we're still in this equation. So just for a moment, I take this apart into two equations so I can find out what x would have to be in each of these binomials in order for one of them to be a factor of 0. So if I solve 2x minus 3 equals 0, I'm going to add 3 to both sides and end up with 2x equals 3. And I know you guys are going to freak out because a fraction is going to result, but I'm going to divide both sides by 2 to get the x by itself. And do not get out your calculator and divide. Just write the fraction. Sorry for sounding frustrated with you. Just write the fraction. I know what some of you are going to do. X equals 3 halves. Over here, I've got to find out what would x have to be to make this binomial factor 0. I have to subtract 4 from both sides. Well, that's pretty clean. Negative 4. So the solution set for this one is 3 halves or negative 4. If x is equal to 3 halves, then the first binomial term would be 0. If x is equal to negative 4, then the second term would be 0. If either of them is 0, then it makes the equation true because of the multiplicative property of 0. All right, one more example. One more glorious example. 18y cubed plus 8y plus 24y squared equals 0. Well, I see, remember, first step, look for greatest common multiple or factor in these monomials. Okay, the greatest common monomial factor is going to be, looks like 2, and what degree of y? Yep, just 1. So 2y, and if we do 18y cubed divided by 2y, we get 9y squared. 8y divided by 2y, we get 4. 2y squared divided by 2y, we get 12y. And this whole thing still equals 0. I'm looking at my chicken scratch again, trying to read what I did here. Yeah, I did that right. Okay, good. So now this isn't in standard form. Let's make it in standard form. The 9y squared is in the right place. But this 12y should be in the middle, and our constant should be the last term. Makes it easier for you to recognize how to factor it. Okay, so if I factor this, this is the same process where you have the two columns and you figure out what your factors are going to be by listing them here and multiplying them times each other. If you do all that work, in the interest of time, I'm going to show you what the answer is because you all know how to do that. You end up with 3x plus 2 times 3x plus 2. You would have listed your factors of 4 here. You would have listed your factors of 9 here and decided which ones, when multiplied times each other, using FOIL here, would give you this trinomial. So we factored it, and now we're left with 2y times 3x plus 2 times 3x plus 2. I have to solve each of these terms in an equation where 0 is the answer. I've done that. And when I solve that, y must equal 0 in this one. And here I have to subtract 2 from both sides, divide both sides by 3, and I end up with negative 2/3. So I see there are two answers in the solution set with my ugly brackets, 0 and negative 2/3. Very good. Well, I've already shown you your homework. I'm going to go back up to it in case you didn't write it down. Here it is. (232, 11 to 23 odd), and the chapter review. All of the problems. Show your work. The odd numbers are, of course, in the back for the chapter review, just as they are for the homework. So come in with your work graded on either a minus check or a plus at the top beside your total correct out of the total possible. All right. Have a great weekend. We'll see you on Monday.